Good afternoon to all of you. I can see more people have joined in. I'm recording this session now. Are there any doubts or questions from the previous class? Anything that you all didn't understand? Am I audible to you all?
Yes, ma'am, you are audible.
So any doubts or questions from the previous class?
None from my side, ma'am.
Oh. There was another matter till some more people join in. You're supposed to have your first periodical test on 4th October. So, have you all got that timetable yet?
Yes, ma'am.
Okay. So, I think financial econometrics is your first paper. So, for that, I think we can have the first 2 units. So, the first 2 units will cover the introductory part that we discussed about financial markets and then returns, the types of returns which are calculated and so on. And then we can cover ARMA models. Okay, so the entire discussion probably until the end of tomorrow's class, that can be your syllabus for the first test. Is that all right with you all?
Ma'am, could we not include ARMA for this particular tutorial? Because right now we would be also having our placement drive going on. And there are 2 subjects for one particular day that we would have to study. And alongside we would be preparing for placements as well. So is it possible we can reduce the syllabus for this
Uh,
particular tutorial?
See, one thing is that your test is, it's an open book test. Okay, so I don't know if you all are aware of that. It's supposed to be an open book test to curb malpractices and so on. So you all will probably have less incentive or reasons to cheat if, not assuming that you all are cheating, but if something like that happens. So if you have an open book test, then I think it'll be easier for y'all, even if you have 2 exams or tests on a particular day. I think y'all should still be able to manage, and uh, I'll try and figure out how to do it in such a way that you just have to apply the concepts. Since it's open book, you won't be asked pure theory questions where you can just copy what's written. So you'll have to apply whatever you've learned. And I think if you have a fairly good grasp of what has been covered so far, then I think you should still be okay. Do you still feel that way, that you don't want ARMA if it's an open book test?
Ma'am, actually, some of us would be having interview on that day, the people who would be selected. So it would be very difficult for them. So it would, if it is possible, can we exclude ARMA part?
I'm afraid there's very little to work with if we have, if we exclude it completely. So, can I suggest a compromise and that we have only up to AR1? Is that okay with you all? If we just have up to AR1, which includes the stationarity conditions, and then the ACF part for only AR1.
Yes, ma'am. I guess it's
Yes,
possible.
ma'am. AR1 would be fine. Till AR1
Okay.
it will be.
Okay, fine. So then for your first test, this is the syllabus. I'll discuss it again at the end. So you'll have the first unit. I'll share the syllabus by the end of today. If you don't have it already, I was assuming that it's available to you all. Uh, yeah, so we'll have the first unit which covers returns, log returns, then simple returns, all those things. So probably you can expect numericals or basically application questions. And The second unit, we'll just have up to AR1. So you'll have stationarity, what is meant by stationarity, and then AR1, you might be asked to solve a particular difference equation. It will be simple. Okay? And then you might be asked about stationarity conditions or restrictions for AR1 and maybe finding the mean, variance, and so on. Okay? And up to ACF, that will be the end of the syllabus for this particular test. Okay? So I'll mention this again at the end. So I hope everyone's fine with it. Okay, so let's begin today's class. It will be open book, so you don't have to worry too much. So yeah, this is where we had stopped in the previous class. We had begun our discussion of the autocorrelation function for AR2. Okay? So if you have an AR2 process, then we were trying to use a method known as the Yule-Walker method, okay, to find the autocovariances and then the autocorrelation coefficients for an AR2 process. So the method that we usually use here, we are omitting the intercept term, okay, because it generally has no effect on the autocorrelation function. So we omit it. So without the intercept, this is the AR2 process. Okay. Now, the procedure that is used for constructing these Yule-Walker equations is that you multiply the equation, okay, the AR2 equation, multiply it by yt minus s. So both sides will be multiplied by yt minus s, where s assumes various values running from 0, 1, 2, and so on. Okay. So if we do this, first assume that s takes a value of 0. Okay. So you get yt into yt, and the right hand side is also completely multiplied by yt, and then take expectations of this. Okay. Now put s is equal to 1, repeat the same process, okay, multiply this equation by yt minus 1 now. Okay. Since s is equal to 1, you get yt minus 1. So multiply the entire AR2 equation by yt minus 1 on both sides and then take expectations. So keep repeating this process up to lag s, where we are not specifying what the length of the lag is. So equations 2, 3, 4, 5, just repeat the same process. Now by definition, for a stationary series, you have the autocovariances are calculated this way. Okay? You take yt and yt minus s, expectation of yt and yt minus s, okay, that is equal to gamma s. This is the general notation that we use. So the covariance between yt and yt minus s will be the same as the covariance between yt minus s and yt. Okay? And then again, if you lag this observation, which is yt minus k, by s periods again, okay, you will find that the autocovariance is the same as what you had for yt minus s and yt. Okay. This is because for a stationary series, the autocovariance depends only on the length of the lag between the two particular observations that you have. Okay. It does not depend on the precise point of time at which you're calculating the autocovariances. Instead, only on the difference in time or the lag between the two observations. And we denote this by gamma s, the autocovariance. Okay. So these are certain assumptions that we'll use going forward to find out what are the covariances and the autocorrelation functions for an AR2 process. Okay. So these are the assumptions that for a stationary series, the covariance between yt and yt minus s is equal to gamma s. Okay. So depending on what value s is taken, okay, you can write gamma 1, gamma 2, and so on. Then expectation et yt is equal to sigma square. Okay, I hope you all have understood this, how we got this result. If you remember, expectation of or the variance of et is equal to sigma square. Okay, so if you use that condition to find out the covariance between et and yt, you will find it's equal to sigma square. Then expectation Et and Yt minus S we are assuming is equal to 0. Okay? So these are certain assumptions that we make while constructing these Ewell-Walker equations and then using it to find the autocovariances and the autocorrelation coefficients. Okay? Now using the previous equations from 2 to 5, okay, we may form the rest of the equations. Okay? So if you take equation 2, okay, then what you see here, this term on the right, on the left hand side, this is nothing but gamma 0. Okay, you're looking at the variance of Yt or gamma 0, the covariance between Yt and itself. Okay, so you get gamma 0, which is nothing but the variance of Yt. Now this term gives you the covariance between Yt and Yt minus 1, which you can denote by gamma 1. Okay, so that's what you see here, A1 gamma 1. Then similarly for this denotes a covariance between Yt and Yt minus 2. Okay, so this gives you gamma 2. Okay, and this is equal to sigma square from our assumptions. So that's how we've written equation 6. Okay. Now for equation 7, again we can just repeat the same procedure. I'll just go through this one, the rest I'm sure you all will be able to follow. Okay, so this one, if you take equation 3, this gives you gamma 1, okay, this gives you gamma 0, this gives you gamma 1 again, okay, and this is equal to 0. So this is what you get, gamma 1 is equal to A1 gamma 0 plus A2 gamma 1 plus 0. Okay, that's why we haven't written it. So this way, using equations 2 to 5, you can form the autocovariances. Okay, all the gammas denote the autocovariances from lag 0 up to lag S. Okay, I hope you all are following me so far. Now after this, we take equation 7 and equation 9 and divide it by gamma 0. Okay? I hope you all are able to see the equations. So we take equation 7 and equation 9 divided by gamma 0. So first we'll take up equation 7. Okay? So here gamma 1 divided by gamma 0 gives you rho 1. Okay? The autocorrelation coefficient at lag 1. Then gamma 0 by gamma 0 is equal to rho 0, or rho 0 is basically equal to 1, okay? Since it's gamma 0 by gamma 0. Then this one gives you again gamma 1 by gamma 0. Okay? So you get rho 1. So this is how we got this particular equation. Then again for equation 9, okay? This is what you will get. Okay? Gamma S by gamma 0 gives you rho S, the autocorrelation at lag S. Gamma S minus 1 by gamma 0 will give you rho S minus 1. Okay? The autocorrelation coefficient at lag S minus 1. Similarly, dividing this by gamma 0 gives you rho S minus 2. Okay? That's how we got equation 11. So now let's take this one up. Okay? When we divided equation 7 by gamma 0, this is what we got. So if you simplify this further, okay, since we know that rho 0 is nothing but gamma 0 by gamma 0, you get 1. Okay? So rho 1 is equal to A1 plus A2 rho 1. Okay? Now if you simplify this further, since rho 1 is common, okay, what you will find is that rho 1 is equal to A1 by 1 minus A2. Okay? So we've been able to find out what is rho 1. Okay, this is for an AR2 process, just remember that. Now this is the equation for rho S. Okay. Now for S is greater than equal to 2, okay, what we find is that by solving the difference equation in 11, we can find all the rho S's. Okay. So this, if you observe, again it's in the form of a difference equation. It's a second order difference equation. So if you solve this by using the method that you have learned, okay, that the general solution will have two parts, you will have a particular solution and then a complementary function. So if you use that method to solve this particular difference equation, then you can find all the rho S. okay, for S is greater than equal to 2. So what we know is that rho 0 is equal to 1, rho 1 is equal to this, a1 by 1 minus a2, and rho s we can easily find by solving this difference equation. Okay. Now for rho 2, okay, for example, it will take this form, rho 2 is equal to this. Once you solve the difference equation, this is what you will be able to find. Now for rho 3, this is the answer that you will get. Okay. Now it's not very important for you to actually sit and solve these equations, okay, but it is important for you to know how we are arriving at these sort of values. Okay. Generally, we use a graph of the autocorrelation function. It's basically a plot of the autocorrelation coefficients against the lags. Okay. So throughout your work, whatever work you'll be doing empirically, what you'll be doing is looking at the plot and then identifying, is it an AR1 process, AR2 process, and so on. Okay. So this, trying to solve this and find it out, it's not very important, but it's important for you to know how we are able to find out the autocorrelation coefficients. Okay, that's why we are doing this. Now for the correlogram, this is basically the autocorrelation function. It's also known as the correlogram. For an AR2 process, you will find that the rho s, the sequence of autocorrelation coefficients, they must be convergent. Okay, which means that gradually the value of the autocorrelation coefficients, they should gradually keep reducing and they should become equal to 0. Okay. Now rho 0 is equal to 1 and rho 1 will be determined by this particular equation. Okay. Once you have the second order difference equation for an AR2 process, you will be able to find out what the value of rho 1 is. Now you might be interested to find out what is gamma 0, okay, which is basically the variance of yt, which is the time series that we are considering. So for this, you can use equation 6, okay, since you know that rho I is always equal to gamma I by gamma 0. Okay. You can use equation 6. I'll just go back to equation 6. Okay, so we can use this equation and then find out what is the variance of yt. So this is equation 6, it's just written again. Okay. So here, if you simplify this, okay, what you will get here is this equation. Okay. This is sigma square, you're just bringing this to this side. Okay. You're bringing it to the left hand side and taking this term to the right hand side. Okay. And then you're solving using the known value of sigma square. Okay. Generally, when you're estimating, you'll be able to find out the variance of the error term, okay, from your regression and so on. So you're going to use that to find out what is the variance of yt. Okay. Generally, the software itself will calculate it, but this is how we go about it. Okay. Now here in the second line, what you'll notice is that basically it's just a manipulation of this equation itself. Okay, so we are just bringing out gamma 0, we are taking it as a common factor. So here you're assuming that gamma 0 was there in the equation. Okay, so gamma 1 by gamma 0 gives you rho 1. Okay. Similarly, gamma 2 by gamma 0 gives you rho 2. Okay. Some of you might have understood that already. I'm just explaining in case someone didn't realize how we arrived at this particular equation. Okay. So we're just manipulating the previous equation. And then if you substitute for rho 1 and rho 2, the autocorrelation coefficients at lag 1 and lag 2, we found out what it was at lag 1 very easily. For lag 2, we didn't really solve the difference equation, but the result was given to you. But you can use those two values to find out what is gamma 0. Okay. So if you simplify, then this is the final result which you will get. The software will be doing this for you, but this is how we arrive at the value of variance of yt. Okay. I hope you will have been able to follow this also so far. If you'll have any doubts or questions, you can stop me and ask. So this
No,
is
I think this was even covered last class also, right?
not completely. I think you all were tired, so I stopped at somewhere here. Okay, I
Yes, ma'am.
stopped at this point. Now for an MA process,
Ma'am, just wanted to ask, ma'am, will we keep on going ahead with just the theory, or will we be trying to apply all of this too at some point?
yeah, tomorrow we are doing practicals, okay, which will be a huge relief for all of you, I'm sure. Okay, so there won't be much theory tomorrow. You'll just be applying whatever you've learned so far in tomorrow's class. So tomorrow it's just practicals. In between, I'll explain some theory, okay, just so that you understand. So far we've derived what the autocorrelation coefficients will be for an AR1 process and for an AR2 process. Okay. Now for an MA process, okay, let's try and understand what is an MA process and then look at the ACF for an MA process. Okay. So this is important because the next part we'll be discussing the plot. Okay, we'll be discussing the ACF and another plot. So there, to identify the particular model you're using, it becomes useful. Okay. So take an MA process where you're looking at this particular time series, okay, ET, which is a white noise series. Okay. So it satisfies all these conditions. That's why it's a white noise process or series. Okay, the mean of ET is equal to 0. It has a finite and constant variance. The auto covariances between ET and its lags are equal to 0, okay, for all J and S. Now let's take a particular white noise process, okay, and let's say that it's an MAQ process, okay, which means that we're taking a series, okay, xt, okay, this is the particular time series that we are looking at, and this is nothing but a moving average process, okay, because it depends on ET, okay, which is the error term, and various lags of ET which are multiplied by these coefficients beta I. Okay. And the number of lags that we are taking are Q, that's why it's denoted as an MAQ process. Okay. So the order of this process is Q, it's an MAQ process. Now XT itself will not be a white noise process if two or more of the beta I differ from 0. Okay. Now let's see why this is true. I've just told you the result. We are constructing this time series xt using a white noise error term. Okay? But xt itself will not be a white noise process if two or more of these beta i's, okay, are different from 0. So let's take this particular MA1 process and see whether this is true. Is xt a white noise process or is it not a white noise process? Okay. So here beta naught, we give it a value of 1. Beta 1 is equal to 0.5 and all the other beta I are equal to 0. That's how we came up with this MA1 process. Okay. So this is what I've written here. XT is this MA1 process. Now expectation XT is equal to expectation XT minus S. Okay, can you all verify this for yourselves? Just take a minute and verify this for yourselves. If you take expectation of xt, it is equal to expectation of xt minus s. Okay, what is expectation of xt? What will it be equal to?
Will it be beta naught over 1 minus beta 1?
Think again. If you're taking expectation xt, you're basically taking expectation of this whole term here. Okay? Et plus 0.5, et minus 1. You're taking expectations of this whole thing. So if you break it up, expectation et is equal to 0 because of our assumptions. again expectation et minus 1 is equal to 0, so you get 0. Okay? So expectation xt is equal to 0. I hope this is clear to everyone.
Yes, ma'am.
Okay. Then can you find the variance of xt? Okay, variance. So one condition of stationarity or for a white noise process is satisfied, that expectation of xt is equal to 0. One condition is satisfied. Okay. What is variance of xt? Can you find out and tell me?
Uh, 1.25 sigma square.
1.25 sigma square. Yeah, correct. Okay. So I hope everyone was able to follow how we found that out. Okay, expectation of et square will be equal to sigma square. Okay, again you will be squaring this term, the coefficient beta 1. Okay, so that's how you get 1.25 sigma square. Okay. Now again, if you look at that term which you got for variance of xt, it's equal to 1.25 sigma square. Okay. Sigma square, if you remember, we had assumed it's some constant finite variance, right? So the variance of xt is also constant and finite. Yeah, so a second condition for the process to be a white noise process or stationary process is satisfied. Okay. Now what about covariance of xt? Can you find out what is covariance of xt? xt and xt minus s. Just work it out and try and find out for yourselves. Anyone? What answer do you get?
Ma'am, I'm not sure if I'm correct, but it would be OU variance of xt minus.
Yeah, go ahead. You can take any value for S, okay?
Ma'am, I am getting 0.125.
0.12.
5.
Okay. Which lag did you take?
Ma'am, I just took one previous lab.
One period lag. Okay, I think your answer should be slightly different, but anyone else? What? Somebody else was saying something? Take one lag, it will be simple. Okay, if you take one lag. I'll just give you another minute. Okay. Yeah, anyone? What answer did you get?
Just a second, ma'am.
Okay. Those who are trying, you can take xt and xt minus 1. So for xt minus 1, basically you will get et minus 1 plus 0.5 et minus 2. Okay, that's what it will become. Just let me know once you all finish. I'm still waiting.
Would it be 0.25 sigma square?
Why are you all getting 0.25? Somebody else also said something similar. It's just 0.5, right?
Ma'am, but it's covariant, so we'll have to take a square of it, na? So 0.
See, you're multiplying 0.5 et minus 1 into just et minus 1. Wait, I'll just quickly write out here. I'm just typing it. What is xt minus 1? Oh, sorry, wait. Sorry, there's a correction. The last term is et minus 2. Okay. Since it's t minus s minus 1, right? Okay, that's what it will become. So it becomes et minus 2. Okay, so when you're multiplying, you get et into et minus 1, which is equal to 0. Expectation et minus 1 is equal to 0. Then you get 0.5 expectation of et minus 1 into et minus 1. Okay, so that is sigma square. Then the other terms are all 0. Okay, so your answer should be 0.5 sigma square. I hope this is clear to everyone. Did you all understand now?
Yes, ma'am.
Okay, so does the covariance satisfy the properties for a white noise process? Okay, does the covariance of xt, does it satisfy the properties of a white noise process? Anyone can answer.
Covariance should be 0
Yes,
for white noise to be
process, yes.
correct.
So this third condition is violated, that you can see very clearly, since you have found that the covariance at lag 1 is equal to 0.5 sigma square. Okay? So the third condition for this time series to be a white noise process, that is being violated. Okay? So the covariance is not equal to 0 at all lags. So this is clearly not a white noise process. Okay, so just because we are constructing a time series using a white noise process, a moving average of white noise error terms, it does not mean that the time series itself becomes a white noise process. Okay? So we might have to impose certain restrictions or conditions to make sure that this series is actually stationary, and then we go ahead and look at the autocovariances and autocorrelation function of this particular series. Okay, if you have an MAQ process. So let's consider for an MAQ process, okay, generally it's easy to consider it if we take a MA process of an infinite order. Okay, that makes our work easier. So we'll use that and then examine what are the conditions for this process to be stationary. Okay, and then once we've derived the conditions for this process to be stationary, we can generalize it to an MAQ process which can be of any order. Okay. So now let's look at expectation of xt itself. Okay, so remember that we are taking a moving average process of an infinite order. Okay, so you have many of these ET terms, okay, up to infinity. Okay. So when you take the expectation of xt, okay, you're taking an expectation of these moving moving average error terms basically. Okay. So all these are equal to 0. If you take the expectation of these error terms, you will find that all are equal to 0. So expectation of xt is equal to 0. Okay. So one condition for stationarity is satisfied here, which is that the mean is constant. In this case, it's 0. Okay. Constant and finite. Then expectation xt minus s also, if you take the expectation at lag s, okay, again you will find that the mean is equal to 0. I hope this is clear to everyone. So one condition for stationarity is satisfied. Now the variance of xt. Okay. So for the variance of xt, just take the expectation of what xt is equal to. Okay. So it's equal to this moving average process. So if you take expectations, what you'll end up with is, since sigma square is common to all these terms, you can bring it out and it will be equal to sigma square into 1 plus beta 1 square, beta 2 square, and so on, okay, up to infinity. Now only if we impose the restriction that the sum of these beta 1s, okay, beta i's are finite, only then variance of xt will be finite. Okay, so for a process to be stationary, remember that we need the variance to be constant and finite. Okay, since we know that this sigma square is some constant, Okay, and the betas itself are some constant. So if the summation of this, okay, beta I square is finite, then we'll know that the variance of xt itself is finite. Okay, so we impose the restriction generally that if you sum up these terms, the sum of these terms will be finite. Okay? Only then the time series will be stationary. Now, if you look at the variance of xt minus s, okay, you will get the same result. Just take a look at it for a moment. Again, in order for this to be finite, the variance to be finite, we need to impose that restriction that the summation of all the beta I squares is some finite value. Okay. So variance of xt and xt minus s, you can see from our derivation itself that it's clearly equal. Okay, both are equal, but we need to impose the restriction that this is finite. Okay. Now, what about the covariance? Okay. So here, if you look at the covariance, again, what you will see is that if you take the covariance between xt and xt minus s, okay, you'll end up with this formula. This is something that you've come across even when we were discussing, I think, AR1, then the wall decomposition. So I hope you're comfortable with it now. So if you find out the covariance, this is what you'll get. Now again, we need to restrict the sum of these to be finite. Okay? The sum of the terms in the bracket, that has to be finite. Only then the covariance will be finite. Okay? Again here, if you look at the terms, okay, you can clearly see that the covariance depends only on the lag, okay, between the two time series and not the precise point in time at which the covariances are calculated. Okay, so here you can see that the term S is coming up, okay, which is the particular lag we've chosen. Again here, the difference between these two is S. Okay, so in each case, you can see that the covariance depends only on the lag at which it is calculated, not the precise point of time. So here also we need to impose this restriction that this term which is coming in the brackets, it has to be finite in order for the covariance to be finite. Okay? So now if you look at all the three conditions, okay, we found that the mean of xt, expectation of xt was equal to 0. Then the variance, if we impose this particular restriction, it is finite. Okay? If we impose the restriction that summation beta I square is finite, okay, then the variance of xt will also be finite and constant. Again, the covariance, it depends only on the lag. You can see that clearly from these terms. Okay? And the covariance again will be finite if you impose the restriction that the sum of these terms, which is coming in the brackets here, that is finite. Okay? So if we impose these restrictions, then you find that this process or this particular time series xt will be stationary. Okay? So the necessary and sufficient conditions for any MA process, whether it is of order Q or infinity, okay, anything, it can be MA1, MA2, MA3, any order, for it to be stationary, for this particular MA process to be stationary, we need to impose these restrictions that summation beta I square is finite and that the sum of these terms which come in the covariance, autocovariance, okay, that also has to be finite. Now for MA infinity, these conditions should hold for all S greater than equal to 0. Okay. So these are the conditions for stationarity for an MA process, whether it's of order infinity or of order Q, okay, where Q can take any value. Now you might be wondering why we were doing all this. Okay. This is because when we look at any process, which we'll be doing later on when you're modeling and so on, we need that particular time series to be stationary and then we begin the process of ARMA modeling or ARIMA modeling. Okay. So that's why this part is important. Now for an MA1 process itself, let's construct or find out what the autocovariances are and then the autocorrelation coefficients. Okay, so again you're going to repeat the same process that we used when we were using the Yule-Walker equations. Okay. So this here we are considering an MA1 process. Yt is equal to a moving average of order 1. So here to find out what is the autocovariance at lag 0, which is nothing but the variance of Yt, just multiply this entire equation by Yt, where the lag s is equal to 0. Okay? Yt minus s, where s is equal to 0, then you get this equation. Okay? And then take expectations. Okay? So you multiply this entire equation by Yt itself, since s is equal to 0, and take expectations of it, so you get the first equation. Okay? So here I've written already what it's equal to. Okay? Once you multiply this out, this is what you'll get. Okay? 1 plus beta square into sigma square. I'll just give you a minute to take a look at it. This term here is Yt, this again is Yt. Then for gamma 1, which is the autocovariance at lag 1, okay, again multiply this whole equation, equation 1 by Yt minus 1, and then take expectations. Okay, so we are repeating that procedure here. So if you simplify this, if you multiply it, this is what you will get. Okay, if you're not able to follow at any point, you can stop me and ask questions. Then for gamma s, okay, which is the autocovariance at lag s, again multiply equation 1 by Yt minus s, okay, and then find out what the term is equal to. Here we haven't, you don't get any value because basically all these terms, okay, Et is uncorrelated with Et minus s. Similarly, covariance or expectation Et minus 1, Et minus s minus 1 is equal to 0. So basically you end up with a value of 0. Okay? So now if you just look at it, we are going to use these autocovariances to then find out the autocorrelation coefficients. Okay? So just keep in mind that for gamma 0 and gamma 1 we get some values, but at all other lags you're going to get a value of 0. Okay. So now to find out what the ACF is, just take equation 2, okay, and divide it by gamma 0. Okay. So gamma 0 by gamma 0 is equal to 1. Okay. Then for rho 1, okay, again take this, the autocovariance at lag 1 divided by gamma 0. Okay. So here what you will get is, since you're dividing rho gamma 1 by gamma 0 is equal to 1 plus beta square. Okay. Just take a minute to go through this and try and figure out how you got this result.
Ma'am, could you explain row 1 again?
Rho 1, yeah. So here if you look at rho 1, you're taking gamma 1. Okay. Gamma 1 is this, beta by sigma square. Okay. Now what is gamma 0? Okay. Rho 0 is equal to 1, but gamma 0 is equal to this, 1 plus beta square sigma square. Okay. So that's how we got this term. Both the sigma squares cancel out, then you're just left with beta by 1 plus beta square. Okay, I hope you've been able to follow that. Then for rho s, okay, remember that all the other gamma s's for lags greater than 1 are equal to 0. Okay? So rho s is automatically going to be equal to 0 because of this reason. So now just try and imagine that you're plotting a graph where you're plotting the values of these autocorrelation coefficients. Okay, so what do you think it will look like if you're plotting a graph?
And it would be a downward sloping graph.
Yeah, you're somewhat close. We'll take a look at it again, okay? But basically, at the first lag, you'll find a line reaching the value 1, okay? So here we are not plotting it like how we ordinarily plot graphs, so it won't look like exactly like what you're describing. But yeah, if you connect the points later, I'll show it to you so you'll understand. Okay, it will look something like what you're saying. So basically at 1 you will have a particular point, and then the second one will be something uh, another value. Okay, at lag 1 you will have a particular value, lag 0 is 1. Okay, and after that you don't have any more points in your graph. Okay, just keep this in mind. So there are basically just 2 points. At lag 1 you have a value, lag 0 is 1. We usually don't consider lag 0. Okay? So this will be important later when we are looking at the autocorrelation functions itself. Just try and remember this. Okay? Now for an ARMA PQ process, okay, let's finish this part and then we can take a quick break. Okay? For an ARMA PQ process, okay, again it becomes very cumbersome if you remember what we were discussing. So we usually don't sit and derive the autocorrelation coefficients and the autocovariances itself, okay, but we can simply solve this particular equation, okay, this particular difference equation. We can simply solve it by using the lag operators. So if you remember how we were using the lag operators from the previous class, okay, this is an ARMA PQ process where the number of autoregressive terms is P. Okay, so there are P lags of YT. And similarly, there are Q lags of ET, the white noise error term. Okay. So here, this ARMA PQ process, we can easily solve for YT, solve this entire difference equation, which is a stochastic difference equation, using lag operators. Okay, so if you use the lag operator notation, what you'll be doing is taking this term, YT minus I. Okay, all these terms you'll be taking to the left-hand side. So when you're using the lag operator, it becomes this, okay, 1 minus summation ai L to the power I. Okay, so since you're going to take lags running from 1 to P, just remember that you'll have P lags here, A1, A2 up to AP. Okay. Similarly here, you'll still have the constant term or this intercept. Now instead of this, again we use the lag operator. Okay, it's not written in that form here, but you can also use the lag operator for this. Okay. So here yt, if you solve for it, okay, it will simply be a naught plus these error terms divided by this. Okay. So this is similar to what we did for AR2. So generally for higher order equations, where you have a large number of autoregressive terms and moving average terms, we don't sit and solve the equations using the process of iteration and so on. Instead, we simply use the lag operator because it makes our work a lot simpler. Okay? So I hope you'll have understood how we have solved this simply using the lag operator. Now we do not discuss the ACF and PACF, ACF itself for an ARMA PQ process because it becomes very complicated to keep constructing the Yule-Walker equations. You can imagine how many terms there'll be in your equations, right? So we don't sit and derive all those. Instead, I'll just show you later on what the plot of the ACF itself should look like. That will help you to identify what sort of a process you're looking at. We'll just do this one and then we'll take a quick break. Okay. Now for the partial autocorrelation function, there's another term which is used called the partial autocorrelation function. Okay. So here, just remember that in the AR1 model, okay, you have yt being regressed on yt minus 1. Now yt and yt minus 2 are correlated. Okay? How do we know that they are correlated? Because when you calculate what is rho 2, okay, which is the autocorrelation coefficient at lag 2, you will get an answer of rho 1 square. Okay? I don't know how many of you remember the discussion from the previous class. I'll just show you that quickly. Okay? If you remember, rho 0 will be equal to 1, rho 1 is equal to A1. Okay? And rho 2 is equal to A1 square. So that's why we're writing rho 1 square here. I'll just quickly try and show it to you. Not this. Okay, I think it's in the previous set of notes. Just give me a minute. Right, I'm not able to find it, but just try and remember this, that rho 0 is equal to 1, rho 1 is equal to A1, okay? And rho 2 is equal to A1 square. So basically rho S for an AR1 process, it is equal to A1 to the power S. Okay? Yes, here it is. Okay. Okay, so this is what I was talking about. This is for an AR1 process. Okay? So that's why we say that rho 2 is nothing but rho 1 squared. Okay? This will just take 2 minutes. I know you all are probably feeling a little tired. Just 2 minutes and then we'll take a break. Yeah, okay, so in the AR1 model, you can see that yt and yt minus 2 are correlated. Okay? So there's some value that you will get for the autocorrelation coefficient between yt and yt minus 2. Okay? That will be equal to A1 square or rho 1 square. But clearly in this model, you can see that yt minus 2 is not appearing. Okay? So although they are correlated or they are related in some way, okay, they are related indirectly and not directly, because yt minus 2 is not appearing directly in this model. Okay? Now all these sort of indirect correlations are captured by the autocorrelation function, okay, which is what we were just discussing previously. Now the partial autocorrelation function, it shows you the correlation between, in an AR1 model, for example, it will show you what is the correlation between yt and yt minus 2 when you remove the effect of all the terms which come in between them. Okay, so between yt and yt minus 2, you basically have yt minus 1. Okay, so if you eliminate the effect of yt minus 1, then you will be able to find out what is the relationship or correlation between yt and yt minus 2. So we do this using something known as a partial autocorrelation. Okay? So a partial autocorrelation between yt and yt minus s, it basically eliminates the effect of the intervening values of yt minus 1 through yt minus s plus 1. Okay? In certain cases, if you put numbers, you will find that that's why this term has also been included here. Okay? So now to find the partial autocorrelations, okay, what you need to do, there is a more complicated method using Mueller-Walker equations. We will not go into that. So we'll use this far simpler method. Okay, so what you need to do is take the time series yt and then subtract the mean from that particular series. Okay, and construct this new variable yt star. Okay, so yt star is nothing but yt minus the mean of yt, okay, that entire time series that you had. So when you're doing this, you're removing the effect of the intervening variables. Okay, just remember that. Now take yt star and regress that on yt minus 1 star. Okay. So yt minus 1 has also basically been demeaned. The mean has been removed from this. That's why you have this star here. Okay. And this is an error term. We are not using the other notation for the error term because it may not be a white noise error term. Okay. So here, when you look at this coefficient which is associated with yt minus 1 star, okay, this gives you the partial correlation between yt and yt minus 1. Okay. Now, as you might have guessed, okay, the partial autocorrelation between yt and yt minus 1 will be equal to the autocorrelation coefficient itself between the two. Because between yt and yt minus 1, there is nothing that comes in between. Okay. Now, if you look at yt star and yt minus 2, okay, here this value, okay, or this coefficient phi 2, 2, that gives you the partial autocorrelation between yt minus 2 and yt. Okay. It eliminates or it controls the effect of yt minus 1. It removes or nets out the effect of this yt minus 1 term and then looks at the correlation between yt minus 2 and yt. Okay. Now you can keep repeating this process for all the additional lags s. So then you get the partial autocorrelation function. Okay. If you plot these partial autocorrelations against the lags, what you will be looking at is the partial autocorrelation function. Now again, as you might have guessed, okay, for an ARP process, there is no direct correlation between yt and yt minus s for s greater than p, okay, which means that if you're looking at the AR1 model, okay, for S greater than P, which means lags greater than P, here the value of P in an AR1 model is equal to 1. Okay, so if you're taking lags greater than 1, in this case if we take lag 2, then the partial autocorrelation will be equal to 0. Okay. So here in this case, this phi 2, 2 will be equal to 0. Okay. So for an ARP process, there's no direct correlation between yt and yt minus s for lags which are greater than p. Okay. So for s greater than p, phi ss, which gives the partial autocorrelation between a time series and its value at lag s is equal to 0. Okay. So a PACF, basically it will cut off to 0 for all lags greater than p for a pure ARP process. Okay. Just remember this. So the partial autocorrelation, it helps you understand what is the relationship between yt and yt minus s when you remove the effect of whatever terms are coming in between these lags. Okay. So once you move beyond these lags, then once you move beyond the particular order of that process, once you move beyond s greater than p, okay, if you move to this point where s is greater than p, you'll find that the partial autocorrelations become equal to 0. So that's why the PACF, if you're plotting it on a graph, it will just simply cut off and there won't be any values after lag p. Okay. So just keep this in mind. Now we'll take a quick break for 5 minutes and then we'll come back. Okay, so right now by my watch it is 3:37. Okay, so we'll meet in 5 minutes at 3:40.
Ma'am, I had a question.
Yeah.
It may seem silly, but I just wanted to ask, what is partial autocorrelation? Because correlation means it's a strength of relationship between two variables, right?
Yeah.
So either there will be a relation or there will not be a relation. So I'm just confused about the whole term, ma'am.
Okay. See, in the way if you haven't, if it's not clear from the way that I explained it earlier, just remember that when you were studying basic econometrics, you were for a multivariate model, right? If you have more than one explanatory variable, okay, then you will have, let's say, yt is equal to beta naught plus beta 1 x1, then beta 2 x2, and so on. Okay, okay, plus the error term. So then when you're finding out what is beta 1, okay, what you do is control for the effect of x2, right? Okay. You assume that maybe x2 is constant, or you're netting out the effect of x2 and then seeing what is the effect of x1 on yt. When there's some change in x1, what is the effect on yt holding x2 constant? Okay, so that's what we do. That's how we find out what is beta 1. Similarly, for beta 2, we do the same thing. You are going to assume that x1 is being held constant, or you're controlling for the effect of x1 and then seeing what is the effect if x2 changes by 1 unit, then what is the effect on yt, or y1 or whatever.
Okay,
So
so we're reducing one variable to check the effect on another, basically.
yeah, you're trying to neutralize the effect of one particular variable. Okay, so
Okay.
here, when you're trying to look at what is the correlation between yt and yt minus 2, okay, you're trying to eliminate the effect that yt minus 1 will have on this relationship. Okay? Just remember, when you're writing out the equations, if you go back to that process of iteration that we were discussing, if you write yt minus 2, there's a way in which you can write it in which it also includes the term yt minus 1. Okay.
Okay, ma'am. So we'll minus the yt minus 1 from yt minus 2.
You're
No,
not.
no, sorry. Wrong. I was wrong.
No, 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 you're close to it. Basically, what you're doing is when you subtract the mean, okay, which is the method that we are using, you're basically removing the effect of all the other variables, right? Whether
Okay.
it's yt minus 1, yt minus 2, yt minus 3, okay, all these effects are being removed. And then you're looking at the relationship between yt and yt minus s, okay, once you've removed the mean. So basically, you're trying to, in some sense, like how we look at demand, okay, you're holding all other factors constant. It's something similar to that, where you're trying to neutralize the effect of the intervening variables and then looking at what is the relationship between these other variables, yt and yt minus 2. For example, if I take an AR3 process, okay, there you will find that there's some relationship between yt and yt minus 1 and yt minus 2 and uh, yt minus 3. Okay? So basically, if I calculate all these values, if I look at what is the relationship between yt and yt minus 1, okay, I'll just be looking only at the autocorrelation coefficients. Okay? If I use the covariances and then divide by the variance and so on, I can find out what is the autocorrelation coefficient. But instead, if I want to look only at the relationship between yt and yt minus 3, okay, here I want to get rid of the effect of yt minus 1 and yt minus 2. So I'll try and neutralize them by removing that mean, okay, from the entire time series. So then somehow the effect of those two variables, it gets removed, and then I can see what is the relationship between yt minus 3 and yt. I hope you could
Okay,
understand.
ma'am. Now, after your explanation, I could understand it, ma'am. I could
Okay,
visualize it now.
okay, fine.
Thank you, ma'am.
Okay, fine. Let's take a quick break. So the break starts now, all right? It is 3:42. We'll meet at 3:47. Okay? Okay, I hope you all are back. It is now 3:48. So let's begin again. So this was about the ACF and PACF. Now let's see what this will look like. Okay, if you try to visualize it, what will it look like? Just a minute. Okay, let's just go through this and then we'll take a look at that. Okay. Okay, so for an MA1 process, I think I missed this out when I was compiling the notes. So this is an MA1 process. So here what I've done is use the lag operator. Okay, so you can rewrite this using the lag operator. It will be ET into 1 plus beta L. Okay, if you use the lag operator, then if you divide both sides of the equation by 1 plus beta L, this is what you'll get. So as long as beta is not equal to -1, you'll be able to write this. Okay. Now if I expand this term is nothing but this infinite sum. Okay. If you remember from our previous discussion, okay, if I simplify this infinite sum, it will converge to this, okay, basically. So instead of writing this, I'm just writing that expansion. Okay, it's basically a binomial expansion. So if you write this out, you can represent this entire MA process as an autoregressive process. Okay. Now the PACF coefficients will exhibit a geometrically decaying pattern if beta is less than 0. Okay, then decay will be direct, which means that if the betas are negative, what you will see is that the decay will be direct. There will be no fluctuations, okay, in your graph. I'll just quickly show you. I don't think the PACF itself is there. I'm not sure. Okay, so this is the PACF. Okay, so here for an MA1 process, you can imagine that it will be decaying directly. Okay? I'll show this to you again. Yeah. Okay. So if beta is negative, then you will get a directly decaying appearance, okay, for the partial autocorrelation function. Instead of beta is positive, then the PACF coefficients will oscillate. Okay, there will be fluctuations. You will see them on both sides, on the positive side as well as the negative side. I'll show you that graph again, so then you'll be able to see it more clearly. Now, for a stationary process in general, the ACF of an ARMA PQ process will begin to decay after lag Q. Okay. So, if you remember, we didn't discuss the derivation of the ACF for an ARMA PQ process, but this is just one general rule which you can note. Okay. So, for the ACF of an ARMA PQ process, okay, it will begin to decay, or you will find that the values begin to dip after lag Q, okay, which means that your process probably has MA terms up to lag Q. Okay, this gives you that indication. So for any ARMA process, what you will notice is that the decay will begin in the ACF after lag Q. Okay? So this would have clearly told you, since we're talking about lag Q, the decay beginning after that you can identify the MA order of a process using the ACF. Okay. Now, if you use the PACF, what you will see for an ARMA PQ process, okay, the PACF will begin to decay after lag P. Okay. So after lag P, which gives you the autoregressive order of the process, you will begin to notice that there is some decay or diminishing values of the autocorrelation coefficients. In this case, partial autocorrelation coefficients. Okay,
Ma'am, can you zoom in a bit?
This will happen after lag P. Okay. So just by looking at these two statements, what you would have noticed is that the ACF will help you identify the MA order of a particular time series or process that you're looking at. And the PACF or partial autocorrelation function, which is the plot of the partial autocorrelation coefficients against the lags. Okay, so the PACF will help you to identify the AR order of the particular process that you are looking at. Okay. Now, because we do not have the actual population autocorrelation coefficient and partial autocorrelation coefficient values, okay, because we are not aware of the actual values of those parameters, so we use sample autocorrelations in order to construct the ACF and the PACF. Okay. So for a stationary series, you can calculate the mean of the series this way using equation 1. Okay. Then the second equation gives you the variance of the series. Okay. And the third equation, it gives you the autocovariance between yt and its lag, okay, at lag s. So we can use these sample estimates to then construct our autocorrelation coefficients and also the partial autocorrelation coefficients, okay, since we don't have the population parameter values. So in practice, we end up working with these, okay, rather than looking at the actual values of the data generating process. Yeah. Yep. So before coming to this, we'll quickly look at what is the likely appearance of the autocorrelation function and the partial autocorrelation function. Okay. So for a white noise series, how will you be able to identify it? If you have the ACF, which is the plot of the autocorrelation coefficients against the various lags. Okay. All the rho S's, which means the autocorrelation coefficients at various lags where S is not equal to 0. Okay. So remember that the autocorrelation coefficient at lag 0, it will be equal to 1 because it's the variance by the variance basically. So when S is not equal to 0, for all the rho S's, you will find that the autocorrelation coefficients are equal to 0. Okay. This is because the autocovariances between ET and ET minus S are equal to 0 for a white noise process. So your ACF, it will show a value of 1, okay, at rho 0, and then there will be no values at all. Okay. Now for the PACF, all the rho S's will also be equal to 0. Sorry, not rho S's, phi S's. Okay. So all these partial autocorrelation coefficients will also be equal to 0 because there's no relationship between ET and any of its lags, okay, for a white noise error term or a white noise process. So you can imagine what the ACF and PACF will look like. Okay, both will essentially not have anything in the graph. Okay, only at lag 0 you will have a value of 1. The rest of it will just simply be blank. Okay. Now what about for an AR1 process? Okay, so if the first order autoregressive coefficient A1 is positive, okay, then you'll see a direct geometric decay. Okay, and rho S will be equal to A1 to the power S. Okay. So if you remember, rho 0 is equal to 1, rho 1 is equal to A1. Okay. So it includes the case where S is equal to 1. So rho 1 is equal to A1, then rho 2 is equal to A1 square, rho 3 is equal to A1 cube, and so on. So that's why you'll be able to see this direct geometric decay. Okay, so this one might be easier for you to understand compared to the others. But this is the reason for the direct geometric decay, because in every case, A1 will be raised to higher and higher powers. Now, what about the PACF for such a process? Remember that A1 is positive. Okay? Now, the PACF, the first partial autocorrelation coefficient will be equal to rho 1. Okay? Psi 1, 1, that is. Because the first order partial autocorrelation coefficient, it's a mouthful to say, okay? So that's why I'm struggling to say it. So the first order autocorrelation coefficient, partial autocorrelation coefficient, is equal to the first autocorrelation coefficient itself. Okay? And all the other partial autocorrelation coefficients will be equal to 0 for s greater than equal to 2. Okay? So you'll just see a spike at lag 1, okay? And the rest will be 0 for the PACF for an AR1 process where A1 is positive. Just remember that I'm using these terms spike and so on. It will look exactly like a spike, okay, when you're looking at it. Now for an AR1 process where A1 is negative, okay, here you'll see an oscillating decay. And again, the reason for the oscillating decay is that A1 is negative. Okay, this is something that we've discussed in the previous classes. And because A1 is raised to higher and higher powers when you're calculating the autocorrelation coefficients at higher lags. Okay, so that's why there's a decay and it is oscillating. Now the same thing, same explanation applies to the PACF that we used earlier, okay, for this. Now what about for an ARP process? Okay, so where in general, where you don't know what the value of P itself is. Okay, generally you will see that there's a decay towards 0 and the coefficients may oscillate or it might be a direct decay. Okay, we can't be sure of that. But generally if you see an ACF where there's a decay towards 0, then you can be sure that it is an ARP process, okay, where depending on how the decay is looking, you'll be able to identify whether it's AR1, AR2 and so on. And the coefficients may oscillate, the autocorrelation coefficients, they might oscillate. Okay? Now for the PACF, there'll be spikes through lag P. Okay? So up to lag P, you'll be able to see spikes. Okay? And for all other partial autocorrelation coefficients for lags greater than P. Okay? This is what we were discussing when we were discussing the theory. Okay? The partial autocorrelation coefficients will be equal to 0. Just remember this. So up to lag P, you will be able to see spikes for an ARP process. After that, it will fall to 0. Okay? So this will help you identify that it is an ARP process. Because if you're seeing spikes up to lag maybe 3, then it will tell you that it is an AR3 process. Okay? If you look at the PACF. Then let's look at an MA1 process. Okay? If beta is positive, then you'll see a positive spike at lag 1. Okay? On the positive side of the axis, you'll be able to see a spike. And rho s will be equal to 0 for all s greater than equal to 2. Okay? So this is again something that we discussed just now when we were discussing the theory. Okay? We actually derived it. Then if you look at the PACF, okay, here when beta is positive, you see an oscillating decay. Okay? This is opposite to what we were seeing for this case. Okay? Here when you are looking at the ACF, if A1 is positive, you see direct geometric decay. If A1 is negative, you see oscillating decay. Here for betas, okay, which are the coefficients of the moving average terms, you will see that just the opposite is happening. The betas will show, I mean, if beta is positive, you'll find the PACF is showing oscillating decay and phi 1, 1 will be positive. Okay? So this is basically the partial autocorrelation at lag 1. Okay, that will be positive. Then if beta is negative, here you will see direct geometric decay. Okay? And you'll see that the partial autocorrelation coefficient at lag 1, it will be negative. Okay? Same as the sign for beta. Now again, if beta is negative, in the ACF, you'll see a negative spike at lag 1. You might be wondering what I'm talking about. Okay? It might seem really vague and very abstract to you. So I'll show you in a couple of minutes. Once we complete this discussion, you'll be able to see it for yourself. Okay? So there'll be a negative spike at lag 1 and rho s will be equal to 0 again for s greater than equal to 2. Okay? Since it's an MA1 process, for lags greater than 1, you'll see that the autocorrelation coefficients are equal to 0. Now for ARMA 1, if the A1 coefficient, the autoregressive coefficient is positive, you'll see geometric decay beginning after lag 1. Okay? So after lag 1 itself, you'll be able to see geometric decay beginning, okay, for an ARMA 1 process. And the sign of rho 1 will depend on both the autoregressive coefficient as well as the moving average coefficient. Since you have only one autoregressive coefficient and one moving average coefficient, so your problem is relatively small here. Okay, you will be able to identify the sign easily. Now, if A1 is positive again, okay, in the PACF, you will be able to see an oscillating decay after lag 1. Okay, so in the ACF, you see geometric decay beginning after lag 1. In the PACF, you see oscillating decay after lag 1. Okay? So a combination of this should help you identify that you're looking at ARMA 1. Okay? Now, the first partial autocorrelation coefficient will be equal to 1. Okay? This is similar to what we discussed for AR1. You can see it here. And the sign of all the partial autocorrelation coefficients will be the same as the sign of the first order partial autocorrelation coefficient. Okay. It's a little abstract, it might seem a little difficult, but I'll give you a shorter summary of this when I'm sharing the notes with you all also. Okay. Now for ARMA 1, okay, if A1 is negative, so here you'll see oscillating decay beginning after lag 1 in the ACF. Okay, because of this negative coefficient. Again, the sign of rho 1 will be equal to the sign of A1 plus B. Okay, basically this means it depends on both. Okay, if you add these two up, what is the sign of the value that you're getting? It depends on that. Then if you look at the PACF, if A1 is negative, what you'll notice is that there's a geometric decay beginning after lag 1. Okay? So this should help you identify that it is an ARMA 1 model, this combination again. Oscillating decay beginning after lag 1 in the ACF and geometric decay beginning after lag 1 in the PACF. You don't have to by heart this. I'll present a shorter summary so it will be easy for you to identify. Then again, the first order partial autocorrelation coefficient will be equal to rho 1. The sign of this, all the partial autocorrelation coefficients will also be equal to the sign of phi 1. Okay. Then for an ARMA PQ model, this is again very general because P can take on any value, Q can take on any value. Okay. So we won't get into the specifics of it. You can see either a direct or oscillatory decay which begins after lag Q. Okay, so remember this will help you identify the MA order of the process that you're looking at. Okay, same here, since geometric decay begins after lag 1, okay, this is because of the MA order of the process, it is 1. Okay, similarly here. Now, in an ARMA PQ models, you'll see either direct or oscillatory decay beginning after lag Q. That will help you identify the MA order of the process. And if you look at the PACF, you'll see again either direct or oscillatory decay beginning after lag P this time. Okay? So this will help you identify the AR order of the process. So remember, in all your practical work, what you'll be doing is plotting the ACF and PACF. You'll use the ACF to identify the MA order of the process, and you'll use the PACF to help you identify the AR order of the process. Okay? There'll be some information here, for example, for AR1, which will also help you identify which particular order of the AR process it is. Okay? But in general, we use ACF to identify the MA order, PACF to identify the AR order of the process. Okay, so let's quickly look at a couple of plots here. So then it might become a little clearer what I was talking about all along. Okay, so this is an MA1 process. Okay, they are telling you that alpha is 0.9. Okay, here. I'll just enlarge it slightly so that you can see. So this is stationary. You can see that the process is clearly stationary. They plotted it as a time series. Okay. So you can see that the mean is more or less constant. Okay. Variance also looks more or less constant. Okay. So you can see that it's a stationary series. Then let's look at the ACF, which will help you to identify the MA order of the process. Okay. So you can see that at lag 0, the value of the autocorrelation coefficient is equal to 1. Okay, this is where the values are plotted and the lags are plotted along the x-axis. Okay, so at rho 0 it's equal to 1, which is something that all of us know. Okay, then you can see there's a sharp spike at lag 1. Okay, and then there's nothing else. So remember, this is what we saw when we were trying to identify an MA1 process. Okay. So you can see that there's a positive spike at lag 1. Okay. So it is clearly an MA1 process. Okay. And rho s is equal to 0 for s greater than equal to 2. Okay. This is what you're seeing in the graph also. So this helps you identify that it is an MA process. Now what about the PACF? Does it help us identify in any way? Let's look at what we found in the table. Okay, here you can see some sort of oscillating decay, right? Okay, it is not direct decay, instead it is oscillating decay. So let's see what it says.
Ma'am, I had a query regarding decay.
Yes.
Ma'am, when it comes to decay, does the term completely decompose into 0 or does it remain like constant in infinity, like 0.00 something like that?
See, in certain cases, there'll be, for example, here, if you look at it, it's gradually becoming smaller and smaller, right? Okay. And then at some point, it will become 0. Okay. But that's very far out. This is like 50 lags or close to maybe 49 lags. Okay. So at some point, it will be equal to 0. But you might not plot so many lags. Okay. But just imagine that it's becoming smaller and smaller, the value of the autocorrelation coefficient. If you plot enough number of lags, it will definitely become equal to 0. So here, I hope that answered your question.
Yes, ma'am.
So here we are seeing oscillating decay. Okay, so you can probably guess that beta is positive. Okay? Based on the PACF. It will not always be very clear what it is. Okay, so this is just a rough guide. So this is how it should look in theory. In practice, of course, it might look very different. Okay. So this is an oscillating decay that we are seeing in that particular graph. And they're saying that the first order partial autocorrelation coefficient, it should be greater than 0. It should be positive. Okay. So is that what we are seeing? Yes. Okay. So that is what we are seeing. So we are guessing that beta is positive. I don't know if, yeah, I think this is supposed to be beta. Maybe they've written that autoregressive coefficient, sorry, moving average coefficient as alpha in this. Okay. So here, this is what you see. You can identify that it's an MA1 process using the ACF and the PACF. Okay. It may not always be so clear cut. Now let's try and look at another one and see if we can identify. Yeah. Okay, so again, every time you're doing your empirical work, your practical work, what you'll be doing is first plotting the time series, checking if it's stationary. Okay, so that's what they've done here again. Now this is an MA2 process. Okay, so if you remember that graph, what it tells you is that there should be a sharp cutoff after lag 2. Okay? So here, this is what we are seeing. This is simple because it's already given at the top of the graph. So you might think that it's a piece of cake. So tomorrow when we're doing practicals, we'll try and identify it without really knowing the order of the process. Okay. So that will help you get some experience in identification. So here you can see that we are expecting to see a cutoff after lag Q, okay, which is what is happening. So since after lag 2, there's a sharp cutoff, okay, none of the autocorrelation coefficients are significant. Okay, these blue lines here, they are the confidence bands or the significance bands. They basically tell you that these autocorrelation coefficients, if they move outside these bands, then they are significantly different from 0. Otherwise, they are equal to 0, okay, statistically speaking. So here, since this one is outside 0, this is lag 1, this is lag 2. After that, it is significantly not different from 0. So we can conclude that we are looking at an MA process based on the MA2 process based on the ACF, because after lag 2, it is cutting off to 0. Now, what about the PACF? Okay, it's looking like some sort of an oscillating decay again. Okay. So again, based on this, they are changing the names of the moving average coefficients. I think in this case, it's theta1, it's 0.85. So that's why you're probably seeing this oscillating nature. Okay. So again, you see oscillating decay. And here, did we see, wait, MA2, right? That's what we're looking at. MA2 is not here. But if you look at the last part here, okay, decay either direct or oscillatory beginning after lag Q, that should help you identify the MA order. So that's what we did, okay, when we were looking at the plot. Okay, so this is helping you identify. Now, what about the PACF? Decay either direct or oscillatory beginning after lag P. Okay. So are we seeing here after lag P decay either direct or oscillatory? It's not very clear. Okay, the lag here is after lag 1, it is beginning to decay or diminish, but they've told you that it's an MA2 process. Okay, so we can maybe conclude that there are no autoregressive terms here. Okay, so theta 1 is the first, your beta 1 basically is 0.85, beta 2 is 0.5. Maybe we can conclude that there are no autoregressive terms. I don't have any further information on this. Okay, but this shows you an MA2 process. Okay, so while identifying, generally you will have to use the trial and error method, fit your model, and then see which model fits best, okay, to the data. Now let's look at another one. Yeah, this is ARMA 11. Okay. Does it look stationary to you all? Okay. Here it is, I'm guessing that it is stationary, okay, and then they have plotted the ACF and PACF based on that. Okay. Since it's ARMA 11, this is stationary. You can see that the mean is more or less constant. In the variance, there are more or less similar sized fluctuations. Okay, so you can conclude that it is constant, this particular time series that we're looking at. Now, if you look at the decay here, it is geometric decay that we are seeing. Okay. Based on the ACF, you should be able to identify the MA order of the process. Let's look at that table. Okay. So if you look at this ACF, geometric decay beginning after lag 1. Okay. So this is what you're seeing again in this graph. So after lag 1, there's a gradual geometric decay which is taking place. So that might help you identify that there's an MA term here where the order is 1. Okay. Now what about the PACF? Okay, so at lag 1, there's a sharp spike. After that, there is still a spike at lag 2. Okay. But they're telling you that it is an ARMA 11 process. So probably it is, the model is best fit or best modeled as an ARMA 11 process where there's only one autoregressive term. Okay. If you look at the table, for ARMA 11, you will find oscillating decay after lag 1, or you can have geometric decay beginning after lag 1. Okay, so is that what we are seeing? So here you see oscillating decay beginning after lag 1. Okay, so that's why it's an ARMA 1-1 process. Okay, just remember that for a mixed process where you have AR and MA terms, these graphs will help you identify what is the MA order and the AR order. Okay. Now there are two more. You can take a look at it again. This is again ARMA 1-1. Okay. Now I'm not sure what these are, okay, what these coefficients are. So I'm guessing this must be the autoregressive coefficient. This must be the moving average coefficient. Okay. Again, the series looks stationary. Here you see direct geometric decay, same as what we discussed in the previous case. Again, oscillating decay beginning after lag 1. Okay, so that's why if you look at the previous one, there's a slight difference in the appearance, okay, compared to the previous one because of these coefficients which are different. Okay, now let's check this. Sine of rho 1 is equal to the sine of A1 plus B. Okay, in both the cases, I think it's true. Okay. So here the sine of both the autoregressive and moving average coefficients are positive. Okay, so even your autocorrelation coefficients are at lag 1, it has a positive value. Even in the previous plot, I think, or graph that I showed you, that was the case. Okay, now let's look at the next one. Yeah, okay, so if you look at this one, it's an ARMA 2-1 process. Okay. So identification is easy because you already know what process it is, but just to help you understand. Okay, so here this time series again is looking stationary. Okay, now let's look at the ACF. Here it is showing oscillating decay. Okay. So that will help you identify the MA order. So let's look at the table again. If you're seeing oscillating decay beginning after lag 1, okay, then it's giving you some indication. This is the case where A1 is negative. Okay, but this should help you identify the moving average order. Okay, just remember that. They haven't given you what the values of the coefficients are, but you are seeing oscillating decay. Okay. Now again, here if you look at the PACF, which should help you identify the AR order, you can see two sharp spikes and then decay to 0. So remember that the partial autocorrelation coefficients after lags where S is greater than P, they'll be equal to 0. Okay, so this is helping you identify the AR order here. At lag 1 you have a spike, at lag 2 you have a spike. For all the other partial autocorrelation coefficients, they're equal to 0. So this very clearly is telling you that it is an AR2 process. Okay? And the MA order, you can see the oscillations. So maybe you can conclude that it is MA1. You can try MA2 and keep modeling till you get the best fit. Okay? Now again, there's a particular pattern to this if you look at it. So maybe it's not just a pure ARMA 2-1 process. This is something that I'll discuss tomorrow in more detail. Okay? There might be some other effect operating here other than a pure ARMA 2-1 process. So remember that in each case, in all the graphs that we were looking at, first we made sure that the time series was stationary, and then we checked the ACF and the PACF to identify the MA order and the AR order. Okay. I hope this was helpful to you all. Tomorrow when we are doing the practicals, you will be able to see it for yourself because you'll be doing it. Okay. Now let's quickly go into the whole process of modeling ARMA models or ARIMA models. Okay. So generally ARIMA is the case where the time series is not stationary and then you transform it in
Ma'am,
some way.
sorry to interrupt, but can we continue this tomorrow because we have a class at 4:30 and you will also take attendance.
Yes,
I'm
ma'am.
not taking attendance. That's the reason I'm continuing, and I'm
Oh,
not
oh,
taking
okay, ma'am.
attendance. I'm not taking because it gets recorded automatically. Okay, so I'll just be wasting time if I take
Okay, ma'am.
attendance.
Okay, ma'am.
I'll just finish this part and discuss quickly just this one part, and then we'll continue tomorrow. Okay, just this one page. So for model selection criteria, I'll just look at this and then I'll discuss the top part, okay, of this page. So for any sort of ARMA modeling or ARIMA modeling, okay, ARIMA is the case where the time series is not stationary. So then we make it stationary through some transformation, either first differences are used or the trend is removed, okay, any of these things. Even in first difference, you could be removing the trend by taking the first difference. So basically you make the time series stationary and then find the AR order, MA order. So then you get an ARIMA model. Okay? So I'll discuss that in more detail tomorrow when we are doing the practicals. Now, the people who came up with this whole technique of ARMA modeling and ARIMA modeling are these two statisticians, Box and Jenkins. Okay, I don't remember their first names. I think it's George Box. I don't remember his first name. Okay? But they came up with the technique in 1976 in a very famous book which was published. Okay, it's used as a textbook for ARIMA modeling and time series modeling. So they came up with a 3-stage method to model these sort of time series, okay, which have both autoregressive and moving average components. So in the first stage, what is done is identification. Okay, so first, what you need to do is plot the time series. Then when you plot the time series, you'll be able to see if there's a trend. You'll be able to identify if there are seasonal patterns to the time series. Okay, so then you can take appropriate steps to maybe transform your series. Okay, or you can also identify whether it is stationary. If you can see that the mean is not constant, that the variance is changing over time and so on, okay, then you'll be able to identify that the time series is not stationary and then take appropriate steps to make sure that it is stationary. After that, once you ensure that your time series is stationary, what you can do is examine the ACF. Okay, so you'll be plotting the ACF. The autocorrelation coefficients will be plotted at various lags. That will help you to identify the MA order of your process. Okay. Then if there's no MA component, you can still identify the AR order using that particular table, okay, which we discussed. Then PACF is used to identify the AR order of the time series. I think you need to mute yourself. Somebody is speaking or something. Yeah. So PACF will help you to identify the AR order, okay, of the time series. So once identification is done, you can begin modeling, okay, and estimation. So your goal will be to select a stationary and parsimonious model that has a good fit. So when we are talking about this term parsimonious, you try and make your model as limited in terms of the number of parameters that you use. Okay, you use as few parameters or coefficients as possible to model the time series. Okay, and then choose the model that has a good fit. Okay, so when you're trying to identify which is the best fitting model, there are two criteria that we use, which is the AIC, archaic information criteria, and this Schwarz-Bayesian criterion. Okay. So these criteria are used to identify the best fitting model. And once you've done that, your goal is basically to minimize or choose the model which has the minimum value of AIC and SVC. I'll discuss what these are tomorrow. So try and fit a model which has as few coefficients as possible. You don't want to include too many parameters or coefficients, okay? Because although you might model your time series very well, you might be able to mimic the data generating process very well, but still you will have an over parameterized model and it might not give you the best results when you look at forecasting, and it's generally not very good to include too many coefficients. Okay? Now, what about the third stage? So in the second stage, we actually estimate the model and then check what is the criteria for selecting the best fitting model, identify the best the model with the best fit based on the AIC and SBC. Then after that, we need to check whether our model is fine. Okay, so is it free from any sort of modeling errors, or is there any information which has been left out from our model which can help us to actually model this time series better than what we have done. Okay, so in this process, it's not visible to you because of this appearing here. But what we generally do is take the errors from the model and check if they are a white noise process. Okay, do they resemble a white noise process? We conduct various tests to identify whether the errors are a white noise process, and then if they are, then we can be satisfied that our model is good. If it's not good, then we just have to repeat the same procedure by changing things here and there, and then follow this entire three-step process again, okay, till you get a model which is satisfactory, where the errors are white noise, which means that your model is free from any sort of modeling errors, and you've used all the information which is available in the sample to actually model the particular time series that you have. Okay. So we'll stop here. This is the three-stage process: identification, estimation, and then diagnostic checking. Tomorrow we'll do the practical and discuss in greater detail, okay, about all these things. So one last thing before you go, you're supposed to have a test on the 4th of October. So the test will be based on a syllabus which has unit 1. I'll share the syllabus by the end of the day. So you'll have unit 1 which talks about returns, then methods to calculate returns and so on. And unit 2 up to AR1, okay, up to and including AR1. So that will be the syllabus for your test. Okay, and it will be application based, it will be open book. So basically you will probably have to apply whatever you've learned, all this theory you've learned, to solving maybe some problems. Okay? So that will be, your test is for again 20 marks. Okay? And I think it's for 1 hour, I'm not sure, I'll just confirm that. So we'll discuss more tomorrow about the actual process of this Box-Jenkins model selection process. When we do the practicals, please download our studio. Okay, you can download R and R Studio. We'll be using R Studio tomorrow for modeling. So those who already have it, well and good. The rest you can download the latest version of R Studio. I'll share the data set with you all by tomorrow morning. Okay, so you all can be ready so that we can carry out the practical work. So let's meet tomorrow then. Thank you for your time. Yeah, I'll see you tomorrow.
Thank you, ma'am.
Welcome.
Thank you, ma'am.
Thank you, ma'am.
Welcome. Yeah.
Thank you, ma'am.
Welcome.